The bifurcation diagram. If this looks familiar, well done. You've studied some nonlinear dynamics, or you studied the logistic map. I'm going to build this file in Geogebra. It's surprisingly nice quality, although it can disappear easily, and it's surprisingly easy to get the logistic map to create this diagram in Geogebra with sort of some sensible list commands. So I'm going to be playing with this. It is interactive still. I just wanted to prove to you. So let's, for example, if you wanted to zoom in on this interesting region here, we can do that, but we do have to do the animation. Let's let it speed up. It's a nice picture. What is it? How do we build it? Let's find out. There's an interesting point going on here. I think this is called the accumulation point. But hey, if you want to build your own file to explore the wonders of this diagram yourself, then keep watching. It doesn't take that long. Hopefully, in the intro to this video, I was playing with a finished file. I haven't built it yet. I want to try and build it now. I want to try and build a way of looking at the relatively famous bifurcation diagram, or the bifurcation diagram of the logistic map. And if you want to know more about why this functional map is important, I suggest doing a couple of things. Watching some videos is a good start. I did a Numberphile video with Brady. You can check that out. One of these, yeah, let's go up here. Check that out here if you want to watch that, and you'll see actually an older version of the file I used in that video to demonstrate what I'm talking about. Derek at Veritasium also did a very lovely video on this topic. It is an important bit of mathematical and scientific history. This diagram and this function, while it had been used for a long time to study population dynamics, more on that in a sec, it was the first, when this diagram sort of got drawn, it was the first time what we now call chaos theory or nonlinear dynamics was really started studying in earnest. And it's a super important topic. I'm not going to talk loads about the maths because those other videos are available. I want to talk about how I built the file. So first things first, I'm going to open the Geogebra window, which, as I said in other videos, I like the downloadable Classic 5. I can move windows around. There are a few features on this that don't function even in the Classic 6, although Classic 6 looks really nice like on the web versions, and you can run it on a phone and all sorts of things. Anyway, I'm working in this. Knock yourself out, do whatever version makes you happy. I'm going to start by taking the function. So this is the logistic map. I'm going to call it f of x. Geogebra recognises that x is now, it's gone blue because it recognises it's going to be my dummy variable. I need a parameter, which I'm going to call a. A lot of people use lambda for this in the literature, but it's easier to type a. You can type lambda, alt L if you care, but I'm just going to use a times x times 1 minus x. That is the function we're going to use. It's very simple. It's a quadratic function and it has one parameter, which I've called a. Geogebra doesn't know what a is, so it's asked me, do you want to create a slider? Useful way of doing it. It's plotted the function. A moment goes between -5 and +5. I'm going to change that to go between, and this is going to come back to haunt us anyway later, what we allow a to go between. And between 0 and 4, there are reasons for that. I'll explain later, I hope. And I'm going to let it have a very small increment. We're going to change this later as well, but I want some fine detail. So at the moment, I'm just cranking the number of steps between those things to be quite high. And I might care about changing that later as well. We'll get to that. So that's my slider. And it's plotting the function. I actually don't care about plotting the function. I could draw a nice cobweb diagram because I'm going to iterate this function. But that's probably for another video as well. So I'm just going to hide it. The blue hide show button is always there. Maybe it's useful to have this on screen. You can drag an item from the algebra bar onto the Geogebra screen. Let's just change the properties of this text because I like it looking a little bit more algebraic. Some serif formatting makes it look a bit more LaTeX-y. Geogebra will do LaTeX in full, maybe another video on that sometime. So that's it. It's not doing anything, but the text is dynamic, and that parameter is actually some sort of measure of fertility. If this is being used as a population model, which is what it was in lots of biological modeling, we can make a bit of sense of it. So x is the population of, let's say, some rabbits between 0 and 1. So 0 being they're all dead, and 1 being full population, whatever that means. So it's a percentage or a fraction, if you like. And it would make sense if you put a number into this. What it's meant to do is tell you what the next generation's population is going to be. Is it increasing, decreasing, what's going on? And it does make sense. First of all, we've got this fertility. The higher the number, the more fertile. And obviously this x is in here. So the higher that x value, which is the population, the higher the next value is going to be, because it's a multiplication thing in there. And that makes sense. More rabbits, more breeding, more rabbits next generation. But there is in this model a slightly more complicated thing, and there's a 1 minus x or 1 subtract x. And that is reflecting that if you have too full a population, we're going to have too much competition for food. Maybe there's not enough food to go round, but a really full population will cause maybe some death, and so the next generation it might go down. So that's why there's a negative x in there. And these balancing forces is what a good simple model does. We could make a different model, but this is a classic one, and the reasons why it goes between 0 and 4 we'll see later on. But if you actually choose an a value bigger than 4, this iteration is not stable. It does not converge. And let's see what I mean with this. So to see an iteration, I could start by using a spreadsheet. I'm not going to build this with a spreadsheet, but you completely could. In fact, the original version of the file I think I used on Numberphile, I did, because it's easy to see what's going on. Let's just say, in fact, I need a starting point for an iteration, so I'm going to call that st. I'm going to start at half. It doesn't really matter where you start an iteration. If it's going to converge, it's going to converge onto its stable behavior almost wherever you start. Almost. So I'm starting halfway between 0 and 1. I could change that later. Since it's Geogebra, I can go and just change that, or I can make it a slider. However, to get the hang of the iteration, let's just say this, get this right, this box is going to be st, so that's my starting population, and the next one, all I want to do is f of the previous cell. It would look like this, and that's done one iteration. And the nice thing about spreadsheet is it lets you iterate really easily. You can see that this population started half full and is now settled down to a value of about 0.62, and changing the fertility changes what it settles down to. And if you're actually not fertile enough, you can see that this population dies quite quickly. And if you copy this down, we've got dead rabbits, and it's very sad, but these things happen. So this is modeling populations dying out and stabilizing, and some other more complicated things which I don't want to give away too much about. I'm not going to do this in a spreadsheet, but that's a nice way to see it, because there's a nice command in Geogebra called iteration, which does maybe what you expect. If you only care about the last value of a repeated iteration, like maybe trying to find a solution and you want to do it 100 times and then look at it, then that's what the iteration function does to a function, or a Geogebra expression if you want to get complicated. I'm not going to do that today. But actually, I care about all the iterations along the way, because sometimes this is not going to stabilize just on one point, and I don't want just the final one. I want the last few points. So I'm going to get an iteration list. So that's the function I'm going to use. I'm going to use the function f, which I defined. I'm going to use a start value of 0.5. And sorry, I'm going to use st because I defined st, and I can change that later. And we're going to have another iterations. Let's make that variable too, n. I want a lot of them because I want to make sure that it's stabilized. So let's just let n go up nice and high. We could go far as 400 and going up in ones. I probably won't change that, but let's just let it go far enough. And you can see already, in fact, maybe if I reduce it, you can see that this list, which I'm going to drag on screen, drag the wrong thing. Let's drag the list on screen. If I increase n, you can see it's just this. It's the spreadsheet basically. It's going horizontally. The curly braces in Geogebra indicate it's a list. And this is a really neat one command way of iterating a function. So I don't want to see that, but it's there. And the thing is, with an iteration, I don't really care about the behavior at the beginning. You can see it starts off at half and it settles down, and actually at the moment it's settling down to I do want to see it, don't I? It's settling down to a dead population. If I change the fertility, you can see it settles down somewhere else. But the beginning, it doesn't settle down. This one's set down pretty quick, but it doesn't always. So I don't really care about the first few iterations. So there's a useful command to deal with that in Geogebra. That's called the last command. And you could just take the last element of a list. In actual case here, I want the last few elements. Maybe I'm not even sure how many I want. So I'm going to say the last of L1, but let's have a different slider for the number of elements. Maybe the last 50 iterations, just in case it's still bouncing at sort of 50 times. But I'm going to make a slider for that. Let's let it go up to from 1 to 50. 100, and we'll probably set it around 50. We can tweak this later on, but the nice thing, particularly if you go and make this file, is that you can go and tweak it if you've built in these variables at the start. So we can let n be 50, and you see that L2 is it's the last 50 elements of that list. You can't tell because they're all the same, but that's a sign this iteration has stabilized. Okay, what I'd like to do is see them on a diagram, because at the moment I've done nothing except calculate the thing, and the whole point of using Geogebra is that you can get some geometric visual going on. And what I'm going to do is plot on the x-axis the a value of the parameter, and on the y-axis I'm going to plot the stable output. So after it's done a few iterations, the last 50, where are they on that vertical scale? And it will be between 0 and 1. So I'm just going to hold down Shift and drag the axis. Make sure I'm looking at the range between 0 and 1. There's a better way to zoom in if you want in a hurry, and I'll show you that in a bit. But I'm going to let this go between 0 to 4 roughly. So we're filling the screen nicely with what we want. And let's get some points. So I want a list of points because I want about 50 of them. I want all the points in L2 here, the last 50 of the iteration, plotted alongside the A value. So I'm going to use the zip command, which is a good way of handling lists, to zip together that list. It doesn't need to be zipped with another list, but it could be. I'm going to make a point, which is going to have an X coordinate of A and a Y coordinate of the values from that list. So I'm going to call that capital Y. It's a dummy variable. As long as I haven't used capital Y somewhere else, it should be fine. And I'm telling it to now to get the Y values from the list called L2. And we should see some points on the screen. There they are. And actually, it's all settled down to 1 point. If I move around, you can see this. Oh, that's them dying off if you're not fertile enough, and that's the stable behavior. And the interesting happens. This is when you start hitting what they call, I think in America, pay dirt. After 3, it does split, and then something mysterious happens. A little glimpse of it. I don't want to spoil it too much. Slight aesthetic thing. I just want to trace it. But maybe these are going to be super blocky. Let's just trace it for now and see what happens. I'm dragging A with my hand. Those are the dead values. Those are the stable values. And it should split at 3. And then it goes into that. So that's kind of where we're going here. If this diagram is unfamiliar, then you haven't seen the bifurcation diagram before. It doesn't look great, but I'm already smiling because what happened at the end there. The rest of this video, to be honest, is making this a little bit more aesthetically pleasing. So a couple of things. Traces disappear. I just rolled my mouse wheel once there and everything disappears. So traces are very ephemeral. I don't think I use that word in any other circumstance, but the trace on a Geogebra disappears as soon as you drag the window or zoom. And that's fine, but it means that it's a little bit sort of fragile, so you can lose an important diagram. However, luckily I can just drag this and get it back. Or Control F also refreshes the page, but I could just animate this and you can see that the animation speed of this slider is actually going to control quite a lot of what we see. It's much smoother if I let it animate it better than my dragging. But there are some blockinesses, and the points are large, so we're not getting a very, very good sort of small pixels resolution. So let's deal with those things now. I'm actually going to hide N and M because I don't think I need them very much. So let's clear the screen. These are the points. Let's change the properties to them. I'm going to make them black. I'm going to make them small, so they're kind of more pixely. And I'm going to make them filled because that's like a little outline option. That is now more filled. Let's just check what's happening there. Clear the screen. When they're selected as well, you get a little highlight around them. So if I deselect them and clear the screen, they're much smaller now. And now let's just animate it again. Right click, animate. Already I can see the gaps between them. So the iterations or the speed of that slider, sorry, the increments or the speed of that slider are affecting that sort of bittiness. Already it's looking interesting though. I would like to make this look better. So maybe what I need to do is slow the animation down. So the properties of this slider are important. The speed here, I can make it just go 10 times slower. I'm going to automate this later. Let's just make it increase each time as well. The increment is small, but the fact that it's trying to move it that quickly means it's not doing every one of those increments. Let's just reset it, clear it again. Let's see what happens if I animate it now. Right, it's going really slowly, but it is not leaving gaps, which is a better sign. So if I just jump to the interesting bit, you see dragging it leaves gaps. If I jump to about here, let's see what happens if I animate this. Right, I have to sort of wait for it to render. It's a little bit like going back in time to when I had a Amstrad CBC 6128, which had a disk drive, but most of the time I was loading stuff off tape. You have to wait for the things to load, and it was loading screens like this. And I was like, why bother loading a screen? I just want to play the game or something. Anyway, I'm talking because this is taking time, but it is a nicer image of an interesting thing. Okay, there's a few things I want to do. I'd like to be able to control the sort of resolution of this. So maybe have a slider for the speed of this so I can choose when it goes quick and when it goes slow. And maybe the increment should be adjustable too. And in particular, I want to be able to zoom in on interesting bits. But if I do zoom in on the interesting bit, like over here, most of the A values are irrelevant to me. So what I'd like to do is get the A slider to depend on what we're seeing as well. So not to fill up loads of sort of empty screen off screen. So those are my three things now, but the build is basically done. It's just aesthetic controls now. First things first, zooming in Geogebra is nice. You can just roll the mouse wheel. Things disappear though. So let me just get a quick sketch, drag it around. That's the region that I'm kind of interested in. If you hold down the right button and drag, you can select things. So actually, if I want to select the points, where are my points? They're over there somewhere. It's selected all those points. That's one way of grabbing. I can just click on the list over here, though. If you built them in a spreadsheet, they'd be all separate points, and you'd have to drag select them. However, that's not what I was trying to do. I want to zoom in on a particular region. Now, there are zoom in buttons, but I never use them. The mouse wheel will do it most of the time. And in particular, if you right-click after you've held down the Shift key, press Shift, holding down Shift, drag with your right mouse button. Now, if you drag in a rectangle, which is roughly the same aspect ratio as your current screen, it will lock to that. This will zoom onto the rectangle I'm dragging. If you drag a different shape, like down here, it snaps out of the aspect ratio you're on, and it will zoom to this region of the diagram. And just to convince you, let me just animate this. It's going nice and slow, but I have zoomed in to the more interesting region, and already I'm liking what I'm seeing. That is a super useful way to zoom into a particular region, particularly if you're zooming into a fractal-like structure like we're going to be doing in this diagram. Unfortunately, the A value is way off the screen. Like, it only goes to 3.25 on the left here, so there's no point in having A over there, so we need to sort that out. Let's just drag it on and let it finish what it's doing here. Gone a little bit early. That's the 2 cycle, and it does it split into a 4 cycle. Oh, it's all very nice stuff. Go and watch the video if you don't know why this is doing this. I'm not sure I answer why it's doing it, but it is fascinating. And it's looking cool. I'm liking this build already. Let's make it a little bit more efficient. So, useful command in Geogebra called corner. The corner command is very useful. If I type corner into Geogebra, it doesn't really give me much help. It just says number of corner. You can choose different graphics views. You can have corners of images and text. Another time we'll talk about that. The corner command on its own normally tells you the corners of the current graphics display. And they are numbered. I've got to get this pointing right. So, corner 1, corner 2, corner 3, corner 4. It goes from the bottom left and it goes anti-clockwise. Don't ask me why. It does do that though. There is a corner 5, more on that in a moment, but let's just convince you. I'm going to get corner 1, because that's going to be the bottom left. Let's call it BL for bottom left. Corner 1, we're on only one graphics view, and you can see that it's got the coordinates of the bottom left, and if I move the screen around, we're going to lose our diagram, but it is changing. So it's a dynamic update. It's a really nice way of getting what should be visible on the screen. So let's get the top right as well. Now, between those, we should have all the details of the screen. So that's corner 3. Nice. I will just show you corner 5. This is my favorite thing. If you're creating a Geogebra file and you want to make sure it's the right size or aspect ratio or pixel dimension. Corner 5, I quite often call it dims. I am going to call it dims for dimensions. Is telling me how big the graphics view actually is. Now, I'm trying to record this in HD in a 1920-ish by 1080 window-ish, but the actual graphics view is apparently 1600 pixels by 840 pixels. So it's 840 up there, which means I know there's only 1600 pixels across the graphics view. It's just really useful to know that corner 5 exists. However, what I'm going to do is try and use these corners I've just defined to limit the values of A, because most of these values of A are off screen at the moment. So let's change the properties here. The minimum of this I would like to be the x coordinate of the bottom left. And the maximum I would like it to be the x coordinate of the top right. And that now means, A only works on screen. Now, actually, it goes beyond 4, but there's nothing plotting beyond 4 because this iteration does not converge beyond 4. And you can see my list has gone into infinity there. So maybe I need to actually limit this just to avoid it having it fit. I could say it's the maximum of that top right x coordinate or 4. So it won't go beyond that. And you can write full on algebraic commands in these boxes. And now you can see that, oh, I've lost the screen. But now, I didn't want the max, did I? Did I want the minimum? Think about it. Do you want to talk while actually solving problems? I want the minimum of these two. Do I? Yeah. And we'll check what happens. Now, so it's stopping at 4. That's not wasting any time. And if I go off screen, you see it's going up to 3.93. Yeah, so we've made the A value much more efficient. In fact, while we're at it, what we can do is figure out some sort of resolution question by getting the horizontal range. I'm going to call it the X range, which is going to be the X value of the top right, subtract the X value of the bottom left, and that's going to be the number of, well, that's the sort of coordinate distance between the right and left, 0.93. And there's only 1600 pixels on my screen, so sort of maximum resolution I could try and get here is divide that region into a number of pixels. But let me make another slider called resolution or res. And this would be an attempt maybe to define how many little divisions to divide our region up into. I'm going to go up to 2000. I think that's overkill, right? Because we've only got 1600 pixels. But as a round number, I can change the resolution, and I could use this to define the increment available to slider A. Let's do that. And that way, we won't waste precision. And when we are really zoomed in, we'll get some more precision, I hope. So let's say the increment should be the X range, which is the coordinate distance between the sides, divided by the res, which at the moment is 1170. And hopefully, if we crank that up, we'll see that animating this, it's definitely doing, I mean, it's going slowly, but it's definitely sort of not leaving gaps. Now, if I made it go quickly, we're still going to get gaps, because however much resolution and increment I do, it's going to need to skip over. So if I make it, yeah, you can see it's leaving gaps. So we need another control, I think, for the speed. Let's sort that out and call it SP. Let it go down to 0.01. I try not to let things go to 0, because then it will actually stop for a speed. Let's just go like this. And I can change the speed of this slider A to be actually that variable, SP. It's still going the same speed. Let's just check what it's doing. Yeah, it's a bit gappy, but if I slow it down, we get better. Now, that's going really slow now. So there's a bit of a sweet spot playing with the resolution, and let's make the resolution a little bit, like, it's only 1600 pixels wide, but let's make it slower. And you just have to adjust. Now, this might change depending on your browser speed or your computer speed or your graphics card, but that looks like it's a relatively smooth curve. And if I wanted to just slow it down a little bit more, it looks like we begin to get nice pictures emerging that don't look like they have too many artifacts in them, by which I mean sort of like graphics issues. But it is interesting that there are some bands in there, and that's a mathematical glitch in the system, if you like. Well, there was a 2 cycle here and a 4 cycle here. There was a 3 cycle there. That little window is a sort of window of stability amidst the chaos, technical terms being used there. Right, so these things are useful to play with the aesthetics. The only other thing I really think we should do now is make it easy to stop and start the animation, and maybe make it easy to zoom back out, because at the moment, to get back out to the full system, I have to do this, and I've changed the aspect ratio. So let's do it by hand once at least. I'm using the mouse wheel. I know it's 0 to 1. So again, right, hold down Shift, right drag. That's roughly the region I want. And you see that is a nice way to zoom, but I had to zoom out to get to that. Because the dots are selected, they're all fuzzy because of the thing around. That's a slightly annoying feature. Ooh, we went below 0. It does converge below 0. We'll talk about that later. Deselect these things and the graphics are a little bit finer. So let's make some view buttons. First of all, let's make an animate button. I'm going to use a checkbox to start and stop the animation. You could always do that by right-clicking on it, but maybe this is cleaner. A checkbox is normally used to show and hide objects, which is why it says this thing here. I'm not going to use it for that. I'm just going to say animate A. I'm not going to choose any objects, because that will make them show or hide when I click this checkbox. So it's just a box that does nothing at the moment. Make sure you go back to that move icon before you start clicking on it. Otherwise, you just build more checkboxes. And pressing escape, by the way, always jumps back to that. That's a very useful shortcut. Hovering over escape all the time in Geogebra. Right, animate A doesn't do anything, but introduction to scripting. In every object, you can click on the properties and click on scripting, and a checkbox has an on-update script. This sounds a bit scary, tiny bit of programming, but it's saying if this box gets updated, i.e. someone clicks on it or something else happens, run these commands. And they're just Geogebra commands. This is a bit of Geogebra script, which is just say a bunch of Geogebra commands. In this case, I'm going to use the command start animation. I wish it didn't auto-complete on this like it would do if you're typing into the input bar. Michael Borshards, if you're watching, can we do that? Auto-complete in the scripting window? Anyway, and I'd like the start animation on the slider A, and I'd like it to be true would mean it starts animating, false would mean it stops animating. So I want to grab the value of the tick box I'm doing, which is called itself B. It's a Boolean value. I want to use that Boolean value to determine whether the animation starts or stops. Weirdly, start animation false means stop. In this case, start animation true means start. That's the script. Let's see if it works. Stopped, started, stopped, started. So we've got a nice little tick box control. I can right click drag if I want to move that around. And I would like to make a button to do some view positions. So I can use a button now, and buttons need a script to work. And that's why when you click on them, they say, what script do you want? So let's just do this as full view of the normal window. And I'm going to use a command called zoom in, which takes all sorts of commands. You can use a scale factor just to zoom in, but actually it will also take 4 arguments, which are the min x and the min y, and then the max x and the max y, and it will just make that the zoom window. So what did we go to? I made a little note on another window what we should do. There's different Geogebra windows, so let's have a quick check. I did this. I'm just going to paste it from here. So I've used square brackets. I don't think it matters. I'm going to check on that. Curly brackets or square brackets, braces, whatever. Anyway, so minimum x negative 0.2, so just go a bit beyond the axis, and same with the minimum y, and we'll go up to 4.1, a bit beyond the max, and up to 1.6 to give us a bit of headroom. Maybe I'll reduce that. We don't need loads of headroom. Let's go 1.3, and let's see what that button does. Go back to that move tool, click full view, and it's changed the view. Now notice it's lost my nice trace, but I can turn it on. Let's just crank the speed up for now while we get a quick view of it. And it looks like it's working. It's got a nice view of it. So I can then still right click with shift down, zoom in on the interesting region. It's going to redraw it starting because it's reduced the A boundaries. It's nice. And we're going pretty quick to get an overview. But if I want to go back to the full view, I still like seeing this emerge. Full view, just click it and it's gone back there. It does have to redraw each time. So this is a time to say the obvious thing. This is not the most efficient way to draw the bifurcation diagram. Use Python. Use C++, use something which you can do loops in and just do it really quickly and just plot the thing. But the fact you can do it in almost one line of code and have the dynamic controls on screen as ever makes Geogebra quite useful to play with this sort of thing. And I like it. We can make it look pretty good, particularly if I slow it down and let it do its thing. So we've got a button, we've got animate A. What else do I want to play with? I think that is about it. Let's see if we can make a nice picture to leave this with. So I'm going to zoom in on an interesting region here just after it's gone into its 4 cycle. We'll make it slow down and get decent resolution. And I'm just going to shut up for a moment, and I'll probably fast forward this in the edit so you can see it build. But this is taking its sweet time. I'm just going to right drag that button out of the way so we can see everything. Okay, fast forward, Ben. Back again. There is something nice about watching it emerge slowly, even though you had a bit of a break from the slowness, because you see surprises like that thing just there was a window of stability. It's one of the big windows of stability in the chaos. There was genuinely a 3 cycle happened there. In fact, you can prove, it has been proven, not by me, I haven't checked recently, but you can prove that any cycle size occurs in this diagram somewhere. And actually seeing it emerge slowly does make you pay attention in a different way. So I'm loving the sort of waves that come here. This is a sign that at each particular A value, the distribution of points, even when it looks chaotic, is not uniform. It's clustering around these sort of points where we can begin to see sort of dusty patterns. I genuinely find this beautiful. And actually, it's going to repeat itself now. And maybe I'll speed it up very slightly, but it is going to add a little bit more detail because I think there's some randomness in the way that it's trying to get through the resolution and the increments, so that it's actually picking up slightly different because it's chaotic. Tiny change in the initial conditions will give you a slight difference. Now I can't quite see where it is animating, so I'm going to add one other detail here, which is that x equals a would give me the line, and that's kind of like the updating line. Maybe turn the label off here, and now I've got a little view. So if I wanted to increase the resolution and speed it up, maybe we might be able to add more detail. I wonder if it does add more detail. By the way, sometimes when you yes, it's shading it in a little bit more. I feel like it's getting darker there. Sometimes if you just drag A, the animation will stop and you need to double click that to get it back in. It is sort of, it feels like it's coloring in a little bit more. So, hey, build this, let it go a few times over it, and it starts coloring in what I think is a genuinely beautiful piece of mathematical truth, interest, art, whatever. That's the build finished. I think what I will leave you with, I'll tag it on the end, is a little glimpse of a video I want to do soon. I mentioned it already. I want to do the Mandelbrot set video, but this is connected to the Mandelbrot set. Maybe not surprising because it's to do with iterations and fractal-like structures and stability. Essentially, you're looking at a glimpse of the Mandelbrot set. It doesn't look like it, and I want to show you why this diagram is connected to the Mandelbrot set, and we'll unpack that when we unpack the Mandelbrot set build in another time. So I said I'd show you just a brief glimpse of how this connects to the Mandelbrot. Let me show you. This is the same sort of file that I made before. This time all I've done is color it blue for reasons that will become apparent. You can see some of the sliders are in a different place, but they're the same setup. And I've changed the function from ax times 1 minus x to x squared plus a. It's exactly the same setup, but you can just double click on it and change it. So it was a x 1 minus x. Oh, I didn't like that. You better tell it to multiply because I don't know what a is. There we go. You can see it's up there. But then I just changed it to the most basic quadratic function, which is this one. And the same setup. I've changed the parameter values because it converges in different places. But this, I hope, is familiar if you know anything about how the Mandelbrot set is calculated. We're going to see what happens. So I'm going to let this animate. It's coming down from about 0.5. It doesn't converge at this point, but it starts to converge here. Did I miss it? No, it's happening there. And the reason is because we are working our way along the Mandelbrot set real axis. We're not dealing with complex numbers. We'll talk about how we can get Geogebra to work with complex numbers. It does it pretty well, except in the iteration command, which is annoying. But here is a picture of the Mandelbrot set, and we're working our way along. I've just lost my my trace because it's too ephemeral when I put the picture on, but it started to converge just where that cusp is, and as soon as we hit this cusp of this, we go into a 2-cycle, and that's because in this bulb of the Mandelbrot set we have 2-cycle type behavior. If we go into the next bulb, it splits into a 4-cycle, and you can see that these changes in the behavior are corresponding exactly to as we track along this in the Mandelbrot set. And beyond this region, we get chaotic behavior. However, there is a window coming, the famous little island at about -1.8, and there it is. Right now, you can see there's a little window in the bifurcation diagram. There's a 3-cycle there. So what these diagrams are doing are giving a sort of one-dimensional slice through the Mandelbrot set. What it does mean is that we just did it with a real iteration thing, and the bifurcation diagram of the logistic map is the classic example. You can do exactly the same with the Mandelbrot map. The thing is, you're going to get more picture, as you can see by that lovely colourful background, if you start looking in complex numbers instead of just real. And that's what we should do in another video, because it's a little bit of a pain getting Geogebra to iterate on complex numbers, but it can be done. And as I mentioned earlier at the very beginning of this, the spreadsheet is going to be a useful backup for that, even if we can't use the iteration list command. Hope you enjoyed watching. I love making these sort of things. The Mandelbrot set is close to my heart. A lot of mathematicians will say that, I hope. But the bifurcation diagram is the first thing that people saw. Robert May was talking about this thing back in the 70s, before Mandelbrot ever saw the Mandelbrot set. So this bit came first, if you like, and changed the world of mathematics. Non-linear dynamics is super important. Previously, most people were just studying linear stuff. And as I think Stanislaw Ulam said, it's a weird name for a branch of mathematics, non-linear stuff. It's like studying zoology, but calling it non-elephant studies or non-pachydermology. It's a stupid name because most things in the world are non-linear and interesting and quite often exhibit chaotic behavior. Every quadratic map, for example. And I was talking long enough there to let it get back to that point. It stops converging just at that point there. Right, thanks for watching. If you want to suggest more videos on topics of how I might build stuff in Geogebra, I'd love to hear them. See you next time.